Hello, my friends, and welcome back to class this week here in GSC 109 and 109L, also known as General Physical Science, where we want to be able to communicate and describe many of the phenomena commonly studied in the physical realm. So this week, we are going to embark on a new phenomena. But first, let's take a look and review some of the previous concepts that we've already encountered in this course. First off, I want to thank you, each and every one of you. I've already taken a look at your first rounds of submissions. I have provided feedback, and I find that you are well on your way for being effective science communicators when dealing with the various phenomena already encountered. I want to congratulate you for sticking with the course so far, and that we have plenty more work ahead of us, so that way we can paint a mosaic of these different phenomena. So when we take a look at the course, we have the course divided into three large thematic sections. But these thematic sections are designed to be experiencing the phenomena and then understanding the evidence that allows us and drives our scientific conceptualization. Basically, how do we take something we experience in our day-to-day lives and describe it and then generate evidence using either observations or mathematical formulas to either confirm or deny that phenomena occurred through scientific testing. In this first thematic section, we are learning about motion, unveiling the secrets of that, but along with learning how energy works. In our first week of the class, we asked ourselves a very important question of how is science done, especially how is physical science completed? And we learned about experimental design. How do we test hypotheses and be able to describe what we experience? Then we move forward. We actually take a look at one-dimensional kinematics, basically the movement along a straight line or a axis, a plane. Then we worked on understanding Newton's laws of motion and found that Isaac Newton took a lot of the research done by his colleagues, his peers, and was able to generate themes within that research that helped describe many of the phenomena of motion and be able to generate mathematical equations and observations that help his future scientists and students such as yourself to be able to understand the forces that are applied on objects as they move around and be able to bridge the gap between one-dimensional kinematics into this week's topic, which will be focused around two-dimensional kinematics. So let's journey forth and learn more about this physical science phenomena. That's all about motion, as understanding both one-dimensional and two-dimensional kinematics will help us with more complex topics later in the course. Now, one of the most interesting things that I want to be able to share with you is the sense that the phenomena in science can be found in both the physical and natural worlds. So, as part of my background, I love bird watching. I actually have a hummingbird feeder set up at my house with a little camera that records who's showing up throughout the season. But when I was making this presentation, I started to think about hummingbirds. And hummingbirds are a great way to show you the phenomena of two-dimensional kinematics as both the physical and natural worlds collide. Two-dimensional kinematics involves the study of an object's motion in 2 dimensions, typically on the horizontal x-axis and vertical y-axis, if we are graphing. To explain this concept using the hummingbirds, we can actually take a look at some of the knowledge you will acquire in this week's module. So imagine the hummingbird hovering near the feeders. It moves forward in a horizontal direction to reach the feeder, and just at the same time, it's adjusting its height, a vertical direction or displacement, to align with the feeder's position. Doing this simultaneously in both directions helps us better observe two-dimensional kinematics. The natural world is full of these types of phenomena. In horizontal motion, the hummingbird moves from one flower to another, in this case, the feeders. It covers a certain distance over time, and the speed at which it moves horizontally can be constant or sped up based upon the speed of the wings and its overall motion. The vertical motion is done by the hummingbird ascending or descending to reach the optimal position for feeding. The vertical movement is influenced by gravity, but also, again, a counter force of the bird's wings flapping. The hummingbird's actual path or trajectory is a combination of these two movements, and the resultant velocity is the vector sum of the velocities in the x and y directions. If the hummingbird moves horizontally at a speed of 5 meters per second and simultaneously ascends vertically at 2, the overall speed and direction of the hummingbird can be calculated using formulas like the Pythagorean theorem. But in this course, we continue to use free body diagrams, positive and negative vector displacements, to help communicate this concept. That way we can fact check our evidence. And this gives us a clear understanding how the birds move through space in an easy to digest and communicate concept. And by studying two-directional kinematics, we can predict and analyze a hummingbird's position at any given time, assuming we understand how those variables work. And that is what we are going to learn about in this week's module by taking a look at the natural world, but also the physical world. If hummingbirds aren't your thing and you want something a little bit more explosive to use as your phenomena, we can turn and take a look at projectiles. In this case, fireworks. You see, fireworks also follow the same concepts of two-dimensional kinematics, much like the hummingbirds. When we take a look at the horizontal and vertical motion, we can see that it still follows a path influenced by its velocity and the effects of gravity. In horizontal motion, the firework is launched. Its horizontal velocity will remain consistent, assuming air resistance is negligible. And that means that the firework continues to move horizontally at the same speed throughout its flight, but then, because we're shooting these up into the air, we want to evaluate more variables focused on vertical motion along that y-axis. The vertical motion of the firework is affected by gravity, and eventually it reaches its highest point in the apex, where vertical velocity is 0. And then the effects of gravity start to pull it down, positive and negative when you think about it. And the combined effects of these motions will allow for the formation of what we call a parabolic trajectory. When the firework is launched at an angle, its velocity can be broken into horizontal and vertical components, but the horizontal component determines how far the firework will travel across the sky, but we're more interested in that vertical component because we want to be able to get it up into the air. As the firework moves through the air, it's climbing upwards and slows down and then begins to free fall back to Earth, and then at the height will show its maximum displacement. And at that height, hopefully that firework explodes, giving us a spectacular display. But we can still find phenomena within that explosion as the particles rain down. And that would still be considered movement. We can check our understanding of the phenomena by taking a look at some equations of motion that you may encounter in this module using basic kinematic equations, such as this one for horizontal motion, where x is the horizontal distance, and then the vx is the horizontal velocity, and t will represent time. For vertical motion, y will then represent the vertical distance, vy is the initial vertical velocity, and g will be acceleration due to gravity, and t is, of course, representing time traveled. These equations will help us predict where and when the firework will reach its peak height, how far it will travel, and begin its descent. In context, two-dimensional kinematics explains how the firework is moving along a curved path in the sky, much like the celestial bodies of the planets that orbit the sun, according to Kepler's laws and even Newton's laws of motion. By analyzing this, we can help take smaller phenomena to answer the larger ones that occur all around us. As always, if you have any questions about this week's material, please reach out. You can get a hold of me during open office hours. My lab can be used as a study space for you. You can send me an email, set up a video chat, and I hope you have an excellent day on planet Earth.